Hello community! We have a new architecture that rivals here our transformer architecture. Let's have a look. It happened quite long ago with our traditional RNNs that they had some problems that the new LSTM architecture, the long short-term memory architecture, could overcome. And LSTM introduced three gates: the forget gate to decide what information to discard from the cell state, the input gate that updates the cell state with new information, and the output gate, which determined what the new hidden state should be. But everything changed when Attention is All You Need happened here in 2017 and transformers emerged. And the transformer architecture was the dominant architecture since then. Of course, we had tries from different architectural approaches. For example, here for the state space model S4 or S6, I have some videos, or especially if you have long sequence DNA strands, they tried here if they could use here the member LLM for some personalized medicine. But the idea of the gating, it quite survived. It was rediscovered and reinterpreted in gated state space model in the member. So you see, all those models learned from each other and integrated some of their ideas. And then it happened 2 days ago that a new idea was published here on Archive for an extended, long, short-term memory structure. And this is what they claim will also rival here the transformer architecture. So let's have a look. What is there to understand? Well, of course, we start here with the classical LSTM mechanism from the 1990s. Just for you, we have the forget gate, the input gate, the output gate, and all gate activation functions are sigmoid function. If you want to read this in detail, this is for you. And the update for the cell state procedure, the formula, was a simple formula. Now, as I told you, LSTM improved here on our recurrent neural networks, but LSTM struggled here with three important issues: inability to revise the storage decision, a limited storage capacity, and we could not parallelize it on our computer infrastructure. And now this new extended long short-term memory system has two innovations. It has now an exponential function in the gating mechanism and some enhanced memory structures. Those two elements are all there is to it, and we will have a look in detail to understand why they are and how they increase the performance. Now, exponential gating, it is simple. Instead of the sigmoid function, you have now an exponential function for a more dynamic range of the gating process. It is faster here, especially for complex dependence patterns in the data. We have to use some normalization and stabilization tricks, techniques, to maintain here numerical stability of the system, but this is how we know how to do this. Now, remember the 1990s, the LSTM memory cell update rules here at the time step t. This is all there is. Please focus here on the input gate I at the time step t. We just had a sigma function. For the forget gate at the time t, we also had a sigma function. Now, if you compare this to our latest, just 2-day-old new exponential gating function, you see instead of the sigma, we have an exponential function and a second exponential function for the input and the forget gate. Okay. If we build now our architecture, we have, of course, an extended LSTM block architecture, a residual block. A residual connection, remember, is a neural network that involves a shortcut that skips one or more layers. And we can have here two forms of the projection. We can have a post-up projection, like we have in transformers, with a non-linearly summarization of the past in the original space, which then linear maps into a high-dimensional space, applies there a non-linear activation function, and maps it back to the original space. Or, like in the state space model, we have a pre-up projection where we do everything more or less in the high-dimensional space. Now, for our xLSTM block structure, containing here the matrix LSTM, the more complex form of an LSTM, we will use here the pre-up projection block since the memory capacity becomes larger in a high-dimensional space. And you know, contrary to our transformer, which have a quadratic computational dependency on the context length, our new extended LSTM network have a linear computation complexity with respect to the sequence length. However, we have to trade off now the memory capacity against the computational complexity. Let's have a look. Those are the new formulas for the new matrix LSTM system, the most complex system. We have C is now our memory matrix at the time step t, allows you the network to store here association between different features. And this is exactly what we want. We want the system to learn here all our different features from our training text and all the associations that happen. And you know, like in the attention, we operate here with key value pairs. And then, if we have trained the system, if we have trained here our matrix structure with the gates, if we then come with a query Q at the time t, is a query vector that retrieves the relevant information from this matrix memory structure, and this mechanism is akin to the attention, but embedded within now our recurrent structure elements. These are the formulas, and you see here again, we have here the exponential function in our gate functionalities. And those gates control here the information flow to and from the matrix. Beautiful. So I ask myself, hey, if I have with the transformer architecture here, the attention and the self-attention mechanism here, the core understanding, what is the corresponding element if I look now here at a matrix long short-term memory model? What is it? What is the core idea of the model? And to your surprise, it is called accumulated covariance. Now, what is covariance and what is the accumulated covariance and what does it do? Covariance. The memory matrix C compiles here our comprehensive summary of the relationship between all keys and values encountered and creates here a rich historical record, especially for time series. So, continuously updating here the memory with new associations, areas of C most relevant to the query yield the strongest signal if we now ask here, if we apply a query to our memory matrix, because now we want to extract the relevant information from our memory structure. And we have something like a separability and a clustering that is happening. And if you think about the cosine similarity in the attention mechanism, we have also here a grouping that is similar items in a high-dimensional space, so they are grouped together. Now, if you want to understand covariance from a little bit more mathematical point of view, this is the definition of general covariance. Quantifies the degree to which two random variables vary together. We have two cases, x increases, y increases, we have a positive covariance, x decreases as y increases, we have a negative covariance, and the mathematical expression between the two vectors is exactly this, where the bar indicates here the mean values of our vectors. This is all there is. Now comes an important point. In our new matrix model, the accumulation of the covariance is facilitated now using here a mathematical operation between the key and values, and the authors decided to go with the outer product. And this is a clever idea that has implications. Now, given a key vector k and a value vector v, the outer product, denoted as kv transpose, creates a matrix where each element ij is the product of the eth element of k and the jth element of v, and this operation projects the value into the dimension defined by the key, forming here a covariance-like structure that emphasizes the relationship. Yes. But the concept now of the accumulated covariance implies here a continuous buildup of this structure over time. So every time we feed a new key value pair into the system to learn, it is added. So as you see here, if we operate now with our memory matrix C, the update structure for our memory matrix C now at the time t, if we think about C at the time step t minus 1, is simply that we add here the outer product of our particular key value set. this is all there is to it. And you go on into the training process, and in the end, you have compiled here a comprehensive summary of all the relationships between all the keys and the values you encountered in your training dataset. So you see, this is here an interesting part now that explains in our standard LSTM, the covariance matrix is updated by the outer product of key values accumulating now over time. So this accumulated covariance plays here a similar importance, is here the core idea if you compare it here to the self-attention with the transformer architecture. A little bit more for my green grasshoppers about the outer product. What does the outer product do here in our matrix long short-term memory model? It accumulates here the covariance, and this is so critical here for the effective building here of a cumulative memory for time series. Let's have a look in a little bit more detail if you want to see here how the dimensionality expansion works, how we encode the interaction, and how we cumulative build up here the memory. Have a look at this, read it carefully. What is the effect of this? I show you here the enhanced memory representation, how it facilitates more complex retrievals, and it scales here with the data complexity. And for my very green grasshoppers who told me they want to have a simple example, well, of course. So suppose you have a key vector here and a value vector, and the outer product of these vectors is simply this. And if you look at this, you see that each row in the resulting matrix is a scaled version of the key vector, where the scaling factor is the corresponding element of the value vector. So what this means is that the outer product matrix encodes the value vector in the direction of the key vector. And this is exactly what we are looking for an additional matrix input flow. And this is what it makes it so easy, this system. But we have another mathematical operation, this is called the Hadamard product here. We have here a beautiful mathematical notation. The symbol here denotes here the element-wise or the Hadamard product in the mathematical notation. And of course, we do it here with matrices. How does the Hadamard product work? Element-wise multiplication involves taking two matrices of the same dimension and multiply the corresponding elements together to produce a new matrix of the same size. And yes, you have an idea how this works. Now, how does it now apply here to our gated memory system? This is a simple idea. You have your forget gate, your vector representation here of f at the time t, and this vector contains the values that determine how much of the corresponding information from the previous memory state, t minus 1, should be retained. So each value of f at the time t is a value between 0 and 1, 0 indicating a complete forgetting, and 1 indicating full retention. And then the matrix is here, holding here our information at the time t minus 1. And the Hadamard product is now used here to apply the forget gate to the memory matrix. This is now how we combine here our exponential gating functionality to our additive memory matrix structure. This scales up each element of the matrix by the corresponding element in the forget gate vector. Operation is crucial for selecting and retaining forgetting parts of the memory based on the current inputs and the network's learned behavior. Yes, for my green grasshoppers, a simple example. How does it work? But in summary, we have only 3 mathematical operations that are important. We have the outer product, we have the matrix addition, and we have the Hadamard product. If you want, pause, read in detail where we apply each specific mathematical operation and what is the effect and how they interlink their effects together in our exponential gating in our either single or multiple matrix memory structures. Great. If you want to see how all of this comes together, time step t, a new key value pair is introduced to our matrix LSTM. And now we have those 4 operations. You compute the outer product to form a matrix representation of your new key value interaction. You scale the previous memory matrix using the forget gate via the Hadamard product. You scale the new outer product matrix using here the input gate. And then you just have to update your memory matrix by adding here those two scaled matrix structures. And you might say, hey, wait a minute. This is a new formula. You have not shown us the new formula, and you're right. So let's come to the point. How do we accumulate here the key value pairs that come in here in our input stream in a matrix memory structure C over time? And remember, we're also looking here for time series analysis. Now, the formula is not complex at all. Let's focus here on the first part in yellow. We go through each element, and then we will focus on the second part. So this is called the covariance update rule in a matrix long short-term memory model. Okay, let's start. So we have our new state of the memory matrix at the time step t. Dimension dd, the dimensionality of the keys and the values, and each element in the matrix represents the accumulated covariance between a pair of dimensions in the keys and the values. Then we have our forget gate vector at the time t. You know what it is. Then we have the element-wise Hadamard product operation. And of course, we have the memory structure at a time step t minus 1. This is all there is. This contains all the accumulated covariance of all the key value pairs up to the previous time step. Then we add a second term. Let's look at the second term. We have here the input gate vector at the time step t. And then we have here a very interesting expression. And you guessed it, this is our new outer product that we have of the value vector and the transposed key vector. Hey, wait a second. And yeah, you can read it if you want for more details. And this is the operation how we have our covariance update formula defined here to go here with our gates from a memory state at t minus 1 to memory state at the new time t. That's all there is to it. Now, if we have our beautiful memory matrix learned, of course, you want to probe it here with a query. So when a query vector q at the time t is used to retrieve information from the memory, it is simply multiplied with the current memory matrix C at the time t to produce here a weighted sum of the stored values, where the weights are determined by the similarity between the query and the stored keys. You can see now it becomes so simple because we build up the memory structure in exactly this way, and this retrieval process allows here to assess here the most relevant stored values based on the current query, enabling it to capture here our long-range dependencies. And this is exactly what we set out to do. Now, if you want to see here the complete structure here, this is the original paper. I was focusing only here on the key idea, the key component of this network. You see we have here our query, our keys and our values coming in. And instead, as in the transformer having a self-attention, now we have this interesting interplay of our complex memory matrix with our gates, exponential gating, that control here the influx and the forgetting here of the information. Yeah, of course, we have learnable skip functions and of course we have here pre-layer normalization, as I told you, and stability factors. But what I wanted to focus here on the main idea of this new model. Yeah, and there you have it. Transformers have their self-attention, and this new model works with an accumulated covariance with an exponential gate structure for access to the memory matrix C. This is all there is to learn. Now, if you think about the attention a little bit more in detail and you want to compare it here to the covariance update mechanisms, I have 3 ideas about it. So at first, if you compare it, the covariance update rule operates on a single key value pair at a time, while the attention mechanism in our transformer operates on a sequence of key value pairs. Second, the covariance update rule uses here an additive update to store here the new key value pairs that come in, while the attention mechanism uses here a weighted sum to retrieve here all the values. And third, matrix LSTM uses here a separate memory matrix to store here the key value pairs, while the transformer uses the input sequence itself as the memory. So you see, there is a significant difference to the transformer. But if you want to understand the core mechanism, the core functionality, they are not so far off, those two systems. Now let's come to the conclusion. The authors say, what have we achieved? How far are we compared to the transformers? And they themselves say, just published 2 days ago, at least as far as current technology like the transformer or the state space models go. So they claim here that their technology is comparable in the performance to the transformer architecture and the state space model. Now, since it's just 2 days since this was published, we have to look at this, we have to explore it ourselves, but I think it is interesting. And it is interesting especially since the authors mention here the potential of the impact of this new method, not only in reinforcement learning and time series prediction, but also on modeling of physical systems. And if you think about this, the integration of robotics, that a robot AI would detect with its sensor its surrounding and understand, and it could model here the physical systems of its environment and calculate what will happen next in the environment based on the laws of nature and based on simple mechanical calculations. Now AI gets really interesting because then we are able to combine here the robotic vision with a prediction model, what will happen in its mechanical environment or its whatever environment. And if we can combine this with predict on the robotic side for the interaction and understanding here the expected time series of the physical systems in their evolution based on the laws of physics, now the system will become real complex. But more about this in a later video. I hope it was interesting, I hope you found it informative, and it would be great to see you in a new video.